So we now come to our fourth and final video in this series, making a memory with LTP. Now, it's really quite difficult to conceptualize how you would store all that information in the hippocampus of a complete memory with visual, olfactory, and audio information. But this basic mechanism of LTP, it is in fact used not only in the hippocampus, but in other brain regions as well, where memories are made. And in fact, in some of these other brain regions, it is far easier to conceptualize just how LTP can make a memory. And so in fact, I'm going to these other brain areas to explain how a memory can be made with LTP. And then at the very end of this video, I will return to the hippocampus and make a few final closing remarks about the hippocampus. So where I'm going to demonstrate LTP making a memory, one place is in the so-called reward center of the brain. This is an area of the brain that rewards animals, including ourselves, for behavior that's essential for life. The other center is the fear center, where we store fear memories. So with this, I'm going to now show you how to learn something using LTP. Here's our rat. Now this rat here, it has a reward center in the brain, and in the reward center you find neurons, pyramidal type neurons, and various innervations are coming into these neurons in the reward center. So this is just one example of one of the neurons in the reward center. Now consider this rat here. What we're going to do is give him a little solution, sugar solution. Now he takes a little lick from the sugar, and it comes out that the sweet taste picked up by the receptors, the sweet receptors in the tongue, this ultimately brings information here into the reward center. So he tastes the sugar, and it just so happens that the animal is hardwired for very strong synapses. And by hardwired, what I mean here is that during brain development, these synapses bringing in the taste of sugar, these synapses are made very strong. And consequently, when it's activated here, the taste of sugar, a strong synapse generates a strong excitatory postsynaptic potential in this neuron, and consequently we get action potentials coming along the axon, and ultimately with the release of neurotransmitter in other brain regions, this drives the feeding behavior. Okay, so that is basically what's going on, and this, of course, this is then essential to life, driving feeding. Now let's consider this same rat. He sees cherries for the first time. So here's his visual system bringing in this image of cherries, and this just so happens ultimately to be brought in here by this neuron here synapsing. So he sees the cherries. But in this case, this is a weak synapse. So we get a small excitatory postsynaptic potential, but nothing happens. Nothing happens because it doesn't reach threshold. It doesn't create an action potential. Now, this particular synapse, however, this happens to be a plastic synapse. It can change, and thus I come to this term synaptic plasticity. These synapses that are plastic, they can be increased in strength. So now I'm going to give you same scenario again. It sees the cherries, So here it is. Here we get activation, we get our EPSP again. But in this case, the animal goes up and it takes a little nibble on one of these cherries. And guess what? There's sugar in those cherries. So it tastes the cherries. It's getting this sugar. Strong synapse here. So strong excitatory postsynaptic potential. And we get an action potential. Now these neurons, they've been designed for learning and memory. And so what we're getting here, at the same time that this action potential goes along the axon to drive feeding, it also, we get a back propagating action potential going back into the dendrites. And guess what? We're going to get here then long-term potentiation, because these synapses, these plastic synapses, they possess the NMDA receptor, and the two criteria have now been met. Sees the cherries, that's releasing glutamate into the synapse, plus we have this back propagating action potential, so we have a very strong depolarization of the membrane here, and we get a strengthening of the synapse. So the NMDA receptor begins through calcium that whole signaling cascade leading to LTP. Good. So this rat now, it's tasted just once the taste of cherries. Next time it sees the cherries, so sees cherries, but guess what? We have now a very strong synapse here. So we get a very strong excitatory postsynaptic potential, reaches threshold, action potential, drives feeding. So now the animal will start feeding on these cherries. So the rat has really learned here cherries are good, and it's done it through long-term potentiation. Okay, now I'm going on to the fear center. Going to have a very similar story here. In the fear center of the brain, again, neurons making synapses with neurons bringing in sensory information. Here is our rat, and we're going to give this rat now a so-called foot shock. It's in a cage where we can send a small current through the bottom of the cage, giving it a little electric shock. So a little pain, a little painful shock. Now the fear center, it's been hardwired for pain. So we get this foot shock, we have a strong synapse here, we get a strong EPSP, and thus an action potential going out along the axon to the terminal, various brain regions, and this drives defense behavior in the animal. Okay, now I'm going to show you an auditory input to the fear center. We make a tone, a sound. Here's the tone. Activation here, but this is a weak synapse. And what we find then is a weak excitatory postsynaptic potential. Doesn't reach threshold, nothing happens. Now I'm going to give you a new scenario. It hears the sound. So activation here. We get that small EPSP, but at about the same time we give it that foot shock. So here comes the foot shock, strong synapse here. Here is our strong EPSP. It reaches threshold, we get our action potential, and of course we get the back propagating action potential as well. And what happens here? Well, we have the coincidence again. We have the coincidence of release of neurotransmitter, the glutamate is in the synapse, plus we have a strong depolarization. So the criteria have been met for activation of the NMDA receptor, and what we find is LTP. Okay, now following that, and this is just one time of the coincidence between the pain and the sound, the next time that animal hears the sound, hears the tone, We now have a strong synapse here. The strong synapse leads to a strong EPSP. It reaches threshold, we get the action potential, and we get the defensive behavior, simply through giving the sound. So, the rat has learned here, tones are bad. Just as in the reward center, it has learned cherries are good. And it's done this all through the all this learning is occurring through LTP. Through LTP and the fact that these synapses, they're plastic, they display synaptic plasticity, the strength of the synapses can change. Okay, now to the hippocampus. And I said here it's a bit more difficult to conceptualize how the hippocampus is using LTP to create memories. The thing it's doing here for sure is in all these synapses and changing the strengths of the synapses, it's making associations. It's making associations of the sensory input that is coming first into the cortex and then down into the hippocampus. So here we have it, visual, olfactory, auditory, all the things that go up are involved in making our memories and in putting all of this memory in context with each other. That is what's going on in the hippocampus, and undoubtedly it is occurring through the it's making the associations to make a memory, and all of this is occurring through LTP. Okay, so this brings me to the end of this series of videos explaining a little bit about the molecular and cellular mechanisms in learning and memory. I hope that you have enjoyed this series.